have a love-hate relationship with Jurassic Park. A lot of people in paleontology do. It's an enjoyable film, I can't deny that. Its effects were groundbreaking, and the decision to use CGI instead of stop-motion animation paved the way for widespread use of computer effects in films. On the biology side of things, Jurassic Park changed the public perception of dinosaurs from dusty giant lizards into sleek, unique animals in their own group altogether. And of course, Jurassic Park gave us the Jurassic Park-style velociraptors. These velociraptors are a far cry from what they would have looked like in real life. Real velociraptors would have been much smaller and covered in feathers, like birds. Birds are a branch of dinosaurs descended from animals related to Velociraptor, and birds share many traits with their non-avian cousins. But chances are you've heard that before. By this point, most people know that at least some dinosaurs had feathers. We have fossils showing exactly that, and even the Jurassic Park franchise is very slowly catching on. Even if future films started to coat their velociraptors in feathers, though, there's something about Jurassic Park that doesn't sit quite right with me, that has nothing to do with details about the dinosaur designs or small scientific inaccuracies. It's more about the big picture of the films, especially that first one. The way the films frame science seem to imply that paleontology is all about individual animals or species, and that the goal of a paleontologist is to find the biggest, most impressive dinosaur. But that misses the most important goals of the field. In order to compare how the film portrays science to how paleontology and related fields actually work, first we need to make sure that we're on the same page about what the film actually says. The artistic choices in the acting, cinematography, set design, and script all work together to communicate a message. An easy way to see this is in the difference between Dr. Alan Grant and Dr. Henry Wu. Both Grant and Wu are lead scientists, and both of them oversee other specialists and workers. They have particular tools and laboratory equipment, and although the film doesn't spend much time showing the research process, they each demonstrate a high degree of competency in their respective fields. But you may have noticed that these scientists are not presented in the same way. Dr. Grant's research time is spent outdoors in a fossil quarry, and even when he's not in the field, he dresses casually with a sort of mock cowboy getup. Dr. Wu is confined to a mostly clinical-looking laboratory, and he wears a sterile clinical outfit similar to the lab coat associated with stereotypical scientists. The film makes a choice in how it presents these characters. Dr. Wu plays a relatively small role in the film, and it's more the lab itself that is important in these scenes. These are tools that the film uses to present a unified idea or point, the theme of the piece. Jurassic Park actually has a few themes depending on how you split them up, but the one that tends to stick is that of man's hubris being his downfall, specifically the hubris of scientists.
So the kind of control you're attempting is, it's not possible. Life finds a way.
When you combine these themes with the science that Jurassic Park does get right, and its attempts to draw upon paleontological reconstruction, scientific discoveries like DNA cloning, and scientific terminology to lend the events in the film plausibility, you end up with a message like this, intentional or unintentional. The film suggests modern scientists are mechanical and cold, only concerned with results, but never conscious of the steps they're taking to reach them. The film doesn't call out any specific players or systems that lead to the disaster, but instead treats it as something outside of human control. About paleontology, the film emphasizes the study of specific animals. The film does address the connections between velociraptors and birds briefly, but that's less to show the evolutionary relationships and more to set up the film's velociraptors being fast and smart, like some predatory birds, so that they're scarier later on in the film. This collective concept makes for an entertaining story because it has clear antagonists, a lot of drama, and it's simple. The story is very easy to digest, which is part of why it was so successful as a film. But the real world is not so simple. So, paleontology, and the broader collection of associated fields called paleoscience, is all about understanding the past. Why do we care about the past? Well, because it shaped our present and will continue to shape our future. By studying life history, we can better understand fundamental biological processes that occur through deep time. Predicting the long-term consequences of modern changes in the environment relies on us understanding how similar changes went down in the past. Just like it's not practical to guess what a film is like from its last 10 frames, trying to understand Earth from just its modern biosphere is going to yield an incomplete picture. The rock record is imperfect, but by piecing together the information we do have, we can start to map important trends. Ecology describes the way organisms interact in physical space. It involves the makeup of a community of organisms at a specific point in time, and how they interact with one another. When multiple organisms exist in an environment, they compete for available resources that allow them to survive and reproduce. Evolution describes how populations of organisms tend to change over time, either ambiently or in response to environmental pressure. The physical environment creates situations that are either favorable or unfavorable for organisms with certain traits, meaning certain organisms are more likely to survive and self-replicate. If the traits that allowed them to endure that specific environment are heritable, then the frequency of that trait within the population will increase as long as the environment stays favorable. Ecology dictates the immediate interactions between organisms, which affect how those organisms evolve, which affects how their descendants interact in the future, and the process continues for billions of years, shaping the biological landscape. This ecology evolution loop has played a role in the histories of countless species, including dinosaurs. Tyrannosaurus rex in particular is one of the most well-studied. Paleontologists have applied a wide variety of techniques to T-Rex fossils, from histology of the animal's bones to computer simulations to more traditional measurements and observations. Different scientists in different subdisciplines collaborate to fill in the gaps of the animal's biology, and many researchers learn to use multiple approaches to solve complex problems. One of the fundamental things Jurassic Park misses when it contrasts Dr. Wu and Dr. Grant is that science is interdisciplinary. Work in one area or with one methodology often has much broader possible applications. Study of T-Rex is not just about T-Rex. It's also about the long history of tyrannosaurs that came into North America from Asia. It's about what was happening around T-Rex and its relatives that caused it to evolve that way, and how its evolution affected other species in its environment. T-Rex lived in a time closer to us than its earliest tyrannosaurid ancestors, and some of that shows in the rocks where we find their bones. Not all films need to be realistic. That feels somewhat slanderous for me to say as a scientist, but films are art and entertainment, and how much they reflect the natural world depends on the intent of the filmmakers. I could use my geology degree to explain why a Sharknado is improbable, but I don't think you or I would benefit much from that, because Sharknado is not trying to reflect reality. And that's okay. Sometimes superficial science in pop culture media can still have benefits by normalizing otherwise highly specialized fields of study. When the public is interested in a subject, regular people are more likely to understand the benefits of research in that area and support funding efforts, which in turn means scientists have an easier time conducting and sharing their research. This benefits scientists, but it also pressures us to do better and reduce the barriers of entry that can make science seem like it's only for a select few people. Paleontology in particular is a highly global field with research spanning all 7 continents. Whether you're an active researcher yourself or just an enthusiast, paleontology is for everyone. So I don't really hate Jurassic Park. My work with the public has actually made me appreciate it more over time, and I think the viewing experience is a lot better when you take it for what it is. It's a good movie, it's fun, but it's not a science movie. I think that's an important thing for scientists and non-scientists alike to realize, because Jurassic Park does strive to be seen as more science than fiction.
Wait a minute, how do you interrupt the cellular mitosis?
Can't we see the unfertilized eggs? Alan, this species of Variformin's been extinct since the Cretaceous period. These are dilated.
They
Take
are?
a look. It's pharmacological.
And it isn't, not in the broad strokes, and certainly not for paleontology. This might not have much of an impact if there were more films that captured or at least got a bit closer to the core conceit of the field, but as it is, Jurassic Park is singular, and that's a problem. Future dinosaur media that draws inspiration from Jurassic Park needs to do more than slap some feathers on the raptors and call it a day. The Earth's history is written in stone, and it takes the efforts of thousands of people to read it piece by piece. Both the stories the rocks reveal and the process to understand them can be compelling narratives in their own regard. Films don't need science in order to be entertaining, but there's plenty of science that deserves a film or two.